For years, astronomers hunted for extraterrestrial intelligence by listening for weak radio signals from the cosmos, until something dubbed 3I/Atlas emerged, decelerating as it hurtled into our solar system. According to official accounts, its increasing luminosity ought to follow basic physical laws. However, over a mere 4 weeks, its glow intensified by 5 times more than anticipated. At the same time, spectral analysis uncovers traces of metals typically produced through intense processes rather than occurring naturally, and defying typical comet trajectories. This intruder shows almost no deviation from its path, even while emitting detectable gas. Should 3I/Atlas prove to be in natural formation, none of these peculiarities can be accounted for. If it's artificial, we might have observed our inaugural interstellar probe guided by advanced intelligence. What secrets lurk within these baffling indicators? Generations of radio observatories have combed the heavens for any hint of a manufactured emission, a signal, a murmur, perhaps an encoded summons from distant realms. Yet amid the quiet, a different avenue has revealed itself. From time to time, a tangible entity bridges the vast interstellar void and penetrates our solar neighborhood. If a large-scale technological marker exists at all, it would resemble precisely this, not a broadcast, but a material presence. In the history of contemporary astronomy, just 3 such intruders have been verified. The probabilities are immense. Out of every 100 billion comets orbiting the Sun, only 1 or 2 originate from beyond our star. Every such incursion represents a stellar windfall, an opportunity to encounter something engineered rather than evolved. Conventional SETI strategies, centered on radio waves and laser pulses, presume that advanced societies transmit actively. But suppose the strongest clues are tangible, quiet, and motionless as they traverse the vacuum? Such artifacts can retain data, mechanisms, and even purpose far beyond the lifespan of their creators. In contrast to ephemeral messages, these relics persist indefinitely. They invite examination, quantification, and, with fortunate alignment, direct encounter. The infrequency of interstellar wanderers elevates each sighting to worldwide significance. Oumuamua in 2017, Borisov in 2019, and now 3I/Atlas. Every instance offers a unique glimpse, a relic from an era or location forever out of reach. Their exceptional rarity ensures that even one irregularity holds profound implications. The cosmos rarely grants repeats. SETI's foundational approach was molded by the instruments of its day: parabolic antennas, data analysis, and hunts for anomalies amid static. Yet the arrival of Oumuamua upended the paradigm. Overnight, the quest for technosignatures expanded beyond auditory cues to encompass transient passersby. 3I/Atlas transcends the status of a routine comet. It serves as traveling proof, an envoy from a foreign stellar domain, and potentially, if we scrutinize it with sufficient rigor, confirmation that solitude is an illusion. On May 7, 2025, NASA's Transiting Exoplanet Survey satellite, TESS, detected a dim, swift traveler amid the dense stellar backdrop close to the Milky Way's core. Initially, no notifications were issued. The trace was submerged in a vast array of cosmic noise, its velocity too understated for software alerts, its radiance obscured by countless nearby stars. For almost a month, the entity progressed, methodically recorded in TESS's wide-field snapshots each evening. Layer by layer, these captures built up subtle imprints on storage systems. It took until July 1 for the Atlas survey, operating from its station at Rio Hurtado in Chile, to highlight the outlier. The visitor's illumination had spiked dramatically, multiplying by 5 compared to TESS's initial observation. Still, its location clung to the Milky Way's bustling central swell, an area infamous for concealing fleeting phenomena in full view. The Minor Planet Center registered the report, and soon after, global telescopes redirected efforts to track it. In the ensuing period, researchers delved into historical datasets. The Zwicky Transient Facility and Pan-STARRS yielded pre-discovery frames from late June, documenting the object's consistent path overhead. Hobbyists contributed too, poring over open repositories and uncovering missing segments from June 14 to month's close. Each additional data point refined the brightness profile, exposing an escalation that surpassed straightforward orbital mechanics. The challenge stemmed from the heavens themselves. Originating toward Sagittarius, the object's path rendered it nearly indistinguishable from the stellar clutter by even the sharpest detectors. It was only post-July reveal that the extent of its prior behavior surfaced, unearthed via exhaustive reviews of massive data archives. For the TESS and ATLAS groups, this find unfolded not as an abrupt flash but a gradual ignition, kindled weeks prior to recognition of an interstellar arrival. From May 7th through June 3rd, 3I/Atlas's radiance grew by a factor of 5, a boost that challenges conventional models for far-off comets. Typical orbital dynamics forecast just a mild uptick, perhaps 1.5 times, as it advances from 6.36 to 5.46 astronomical units from the Sun. Yet measurements from TESS, ZTF, and ATLAS indicate a consistent 5-fold rise, enduring over roughly 0.9 astronomical units of motion. Data from each instrument aligns precisely, validated against reference stars and modeled sunlight replicas. Variations in brightness remain below 0.1 magnitudes in systematic checks. This represents no fleeting spike or equipment glitch. The luminosity profile, assembled from evening image composites and drift-adjusted observations, traces a distinct upward curve, even while the body navigates the dense star fields of the Milky Way's core. Positioned at 6.36 astronomical units, such behavior seems improbable. H2O frost remains solid. Solar heat feels remote. Nevertheless, the surrounding haze is detectable, and estimates of dust coverage surge from roughly 300 square kilometers in May to more than 1,700 by July. These figures withstand rigorous examination, featuring error margins narrow enough to dismiss noise or stellar interference as culprits. Aggregating the brightness signals, probabilities veer decisively from mere alignment effects. The surplus illumination calls for an interpretation that aligns with both the schedule and the extent. No individual observation program, however thorough, explains the shift's amplitude fully. The unvarnished evidence allows scant doubt. 3I/Atlas exhibited signs of activity and stood as an anomaly prior to formal cataloging. Probing for resolutions starts at the core data. A quintupling in luminosity, surpassing all alignment forecasts, requires more than a cursory review of the observations. Researchers evaluate standard possibilities, device malfunctions, stellar overlap, or a fortuitous view through Sagittarius's clutter. Each option undergoes verification, scrutiny, and dismissal. The luminosity profile remains consistent over observatories and global sites. It's curve too even for coincidence, and too premature for conventional cometary outbursts. A few proposed the body's actual approach velocity was miscalculated, obscured by Sagittarius's packed stars. Yet, even with adjustments for density and refreshed brightness calibrations, the extra signal endures. The figures fail to align with a typical gradual activation. This opens possibilities for more audacious concepts. Might 3I/Atlas have activated propulsion? A deliberate slowdown to synchronize with solar system speeds? Though it dwells on the margins of theory, the chronology matches the evidence. A managed velocity reduction, performed well beyond solar proximity, could account for the premature sustained glow without invoking water, frost, or standard outgassed materials. In that case, the emissions would signal purpose rather than chance. Still, each adventurous theory faces an anchor of skepticism. The heavens often deceive vigilant watchers, and evidence must bear substantial weight. As discussions evolve, focus moves to the haze's composition, where another hint might lurk openly. VLT spectrometers, sensitive to the subtlest emissions of elemental glow, detected an enigma in 3I/Atlas's envelope. Prominent nickel signatures, sharp and distinct, emerged over the noise. However, iron, expected to accompany it closely, evaded detection. Observers at Paranal devoted evenings to verifying standards, reapplying Turek adjustments, and matching against lab references. The result persisted. Nickel appeared, iron did not. No local comet displays such a disparity. Typically, iron and nickel pair up, bound in bonds from stellar explosions and protoplanet hearts. The Sun's surface contains around 18 iron atoms per nickel atom. In even the grimiest, metal-laden comets, nickel seldom exceeds iron by over twofold. Here, the proportion exceeds 15, possibly 50, with iron signals lost beneath sensitivity thresholds. Under Dr. Sofia Cardenas's guidance, the VLT team charted nickel shifts in standard and enhanced detail modes. Output levels stabilized near 4.6 grams of nickel per second at 2.85 astronomical units, alongside firm caps on iron that pushed the Ni/Fe quotient beyond norms. All efforts to extract a concealed iron trace, layering images, scanning for subtle overlaps, yielded nothing. Conventional processes falter in accounting for it. Breakdown of nickel carbonyl, a delicate compound that sublimes easily, might elevate nickel output, though iron variants form or endure less readily. Certain models invoke targeted erosion or unusual separation in protoplanet formation. More daring voices speculate on artificial remnants, nickel-heavy advanced metals worn by long-gone drives, imprinting the envelope. To date, no exhaust traces or clear fuel/alloy markers appear, just isolated nickel amid iron's absence. The atomic balance tilts oddly, fueling the hunt for earthly causes. By conventional metrics, 3I/Atlas's path poses a riddle. Position measurements from July to August reveal a deviation of only 1 to 1.5 kilometers per day, a mere whisper, despite the envelope and streamer extending hundreds of thousands of kilometers rearward. For inter-system comets, venting functions as thrust. Gas streams divert the core, yielding detectable deviations from gravity. Yet here, the metrics scarcely shift. The route adheres nearly purely to gravitational pull. It seems as though the body is treating the entity like lifeless rock rather than a dynamic comet spewing gases and particles. When we compile the observations, this lack of propulsion influence becomes glaringly apparent. Borisov, the previous interstellar wanderer boasting a prominent coma, passed by at roughly 100 kilometers each day, almost 2 full magnitudes faster. A basic tail ought to have pushed the core slightly, yet 3I/Atlas defies it. Images reveal the anti-tail, the dust particles, and the evident jets clearly. Still, the trajectory holds firm without deviation. Simulations incorporating the documented material ejection and exposed surface area forecast a far greater orbital adjustment. The figures simply don't align. For something composed of frozen water and stone, the sole method to mute this thrust so thoroughly would involve immense bulk, something extraordinarily heavy and vast that even the most forceful ejections could scarcely budge it. However, brightness measurements and surface luminosity analyses impose tight constraints on the core's dimensions. It's substantial, yet within believable bounds. Thus, the other possibility involves deliberate guidance, ongoing adjustments, precise balancing, or perhaps an outer layer that captures or reroutes the momentum. No conventional natural process adequately bridges the divide between visible phenomena and recorded motions. With each new positional measurement, the uncertainty margins narrow further. The motion remains fixed at slightly over a kilometer daily, while under the level where cometary dynamics would anticipate effects. The data speaks plainly. 3I/Atlas traverses the solar system as if shielded from its own emissions. The inconsistency isn't merely numerical, it's fundamentally physical. Among ordinary celestial bodies, paths obey principles of weight and impetus. Here, those principles flex, and the course shows scant variation. Among extrasolar intruders, Borisov exemplifies the standard. Its enveloping haze and trailing streamer, laden with cyanogen and C2 molecules, followed a predictable curve across the inner system. The metrics aligned with predictions. Non-gravitational pull registered around 10⁻⁻⁶ AU per day, equating to about 100 kilometers of daily shift. Each vapor burst prodded the nucleus. Every flare registered in the path. 2I/Borisov acted as a comet ought, heeding the rules of sublimation and solar warmth. Oumuamua, however, ignored established norms. No detectable venting, no particles, no haze. But its route curved noticeably at closest solar approach, with a non-gravitational pull of roughly 2.5 times 10⁻⁻⁴ AU per day. That amounts to 37,000 kilometers of deflection, all absent any jets or streamers to account for it. Its spin, a consistent 3 rotations daily, amplified the enigma. Calculations hit dead ends. Insufficient substance for an icy lump. Excessive motion for solid stone. Now 3I/Atlas joins the record, but flips the script. The coma is unmistakable. The tail extends across hundreds of thousands of kilometers. And still, the detected motion is minimal, just 1:1. 5 kilometers per day. That's a 100-fold reduction from Borisov, a mere sliver of Oumuamua. The propulsion influence vanishes where it should prevail, emerges where it should hide. 3 visitors, 3 behaviors, none sharing a template. The cosmos, apparently, hands out its oddities in contrasting duos. The Vera C. Rubin Observatory awaits on Cerro Pachón. Its 8.4-meter mirror is set to scan the southern heavens every few nights. Through the Legacy Survey of Space and Time, LSSD, Rubin ushers in an age of prompt detection. Its rhythm and acuity ensure the upcoming interstellar arrival, be it a comet or an otter form, won't evade notice amid the stellar clutter. Notifications will issue instantly, offering experts and enthusiasts a head start. Yet instruments by themselves can't unravel every anomaly. The prior 2 intruders demonstrated this. When 3I/Atlas surged 5 times brighter against the Milky Way's core, it was hobbyist stargazers who sifted through vast archives of data, piecing together the initial precise brightness history. A community of volunteer observers, equipped with home telescopes and free tools, bridged the intervals between main surveys. Their swift updates transformed disjointed snapshots into a coherent sequence, spotting outbursts that might otherwise fade into background static. Today, the urgency intensifies. As Atlas nears the sun, each evening matters. Joint efforts, Rubin's regular scans, Pan-STARRS in Hawaii, Atlas in Chile, and observer posts from Pretoria to Perth form a worldwide web. Every watcher contributes a reading, reducing uncertainties, refining predictions. The following surge or odd emission line might strike any time. Initial alerts spread via Discord channels and Telegram chats, sparking immediate pursuits from observatories big and small. The directive is straightforward. Watch the heavens, monitor the brightness plot, pursue the composition analysis, distribute unprocessed shots, and process composites. In this landscape, breakthroughs aren't exclusive to specialists. Each notice, each photo, each datum edges us nearer to grasping the extraordinary. A signal encoded not in signals, but in trajectory, elements, and radiance. Spectra from the Very Large Telescope reveal nickel I within its coma. However, iron was absent, presenting a peculiar compositional profile. Astrometric analyses indicate minimal non-gravitational forces acting on it, despite observable material venting. By comparison, the 2 instances of 2I/Borisov exhibited standard cometary deviations, and 1I/Oumuamua demonstrated notable path alterations absent any signs of emissions. Such conflicting irregularities continue to elude existing theoretical frameworks. Although nothing points to engineered guidance, the inconsistencies in Comet Atlas's dynamics undermine conventional understandings. Perhaps our most valuable insights will emerge not through transmissions, but via celestial visitors whose paths themselves contradict our predictions.